Thank you. I'm very happy to be here. I know that this is my first time in Belgium, and I had a very nice time. Yeah, so I realized there's kind of a range of backgrounds that people have in terms of how geometric people are, and so I'm hoping to give a talk today that will be accessible to the range of people. But in any case, don't hesitate to stop me and ask more questions at any point. Okay, so I'm going to start with a projective variety. And in algebraic geometry, one of the ways that we have to kind of distinguish varieties and how complex they are, by complex I just mean complicated, nothing to do with the complex numbers in particular, how complicated they are is via an invariant called the codire dimension of the variety. And the codire dimension of this variety x can take values in so minus infinity, 0, or any integer up to the dimension of x. Okay, you can sort of see as the number increases, this is supposed to represent an increase in complicatedness of the variety. So for example, if we look at so I'll use this letter k to denote the codire dimension. If we look at the codire dimension of x being minus infinity, so the smallest possible value in this list, we should think of this as some kind of algebra geometric analog of having positive curvature. Right, so in the case of a variety of dimension 1, so an algebraic curve, this actually does exactly correspond to having positive curvature. So if we have a curve and it has codire dimension minus infinity, this actually means that our curve is just P1, which we know is the sphere. So here's my 3D picture of this curve is just S2, which indeed has positive curvature. Right, and similarly, if we think about the next case, so codire dimension 0, we should think of this as a kind of notion of flat curvature. So, for instance, again, going back to this dimension 1 case, it turns out that if I have codire dimension 0 and I have a curve, then I'm actually what's called an elliptic curve. Meaning, topologically, my x is just a torus. Which has flat curvature in some well-defined sense. Yeah.
You said projective variety. Do you mean over some particular field?
Well, over the complex numbers. Yeah. I don't concern myself with other fields.
Can you give me an example of that? Because you said curve for curves, it's really like curvature.
Yeah.
So this is the example of something of positive curvature. The
sphere.
The sphere. Okay.
I mean, this is
example, or is there another example?
No, for curves, no.
Okay.
Okay, and then if I said so, the other kind of example we can look at, especially if we're thinking about dimension 1, right? Then I said, well, the maximum value I can have is the dimension of the variety. So if we think about the case of the variety being the curve, this is just 1, it's our maximum, right? So if I look at codire dimension being the dimension of the variety, this is supposed to be some kind of notion of negative curvature. And in the case of curves, this actually, works formally. So if I look at the dimension of my variety being 1, it turns out that then my curve is just of genus greater than or equal to 2, right? And so topologically, I have something like this. Okay. Okay, so these are sort of the 3 buckets that I'll care about today, right? So things of codire dimension minus infinity, things of codire dimension dimension 0 thinks of codar dimension as the dimension of the variety. And so I want to say a little bit more about these different buckets. You know, if we're thinking about varieties of higher dimension, how should we think of these different buckets, or what are sort of the classic examples of varieties that fall into each of these buckets? So if I'm thinking about this codar dimension minus infinity bucket, what are some classic examples of varieties that fall in this category? Right? I said these are somehow supposed to be the easiest possible varieties, like the least complicated varieties. So what are the least complicated varieties? Well, naturally, any variety birational to some projective space is going to be inside of this bucket, right? But we also have other kinds of easy constructions that give us varieties that fall into this category. So, for instance, another.
No. Is it a birational invariance?
Yes. Is it? So I didn't say that, but correct. The codar dimension is a birational invariant. Hence why, you know, it's anything birational to projective space. Okay, so another class of examples in this codar dimension minus infinity bucket are what are called Fano varieties. So these are varieties where if I look at minus the canonical bundle, so this is, I'm looking at the wedge product of dim x copies of one forms on my variety. That's what I mean. And I'm taking the minus of it, so minus that. This thing is active. Right, so meaning it has lots of sections. Okay, and so an example of such a Fano variety is something like take a hypersurface inside a projective space of low degree. So this is going to be Fano if and only if D is less than or equal to n, the dimension of the space. Okay, and similarly, I can generalize this to complete intersections of hypersurfaces. So I can take an intersection of, you know, k hypersurfaces, each of degree d sub I, and as long as the sum of those degrees is less than or equal to n, the resulting intersection is Fano. Okay, and so hence I land in this bucket. Okay. If I'm thinking about, so these were my kind of positive curvature examples. If I'm thinking about what are my flat examples, right? I said that codar dimension 0 is supposed to be things that are flat, in some, you know, hand wavy sense of the word flat. So what do I have in here? Well, as I said, if I'm looking at curves, I have elliptic curves, which were these, you know, genus 1 curves. If I want to go up a dimension, I'm so sorry, let me say instead, I said these elliptic curves, what's a definition I can do for these elliptic curves is that they're complex tori that also happen to be algebraic varieties. And so I can sort of, if I want to generalize that notion to higher dimensions, one way is to say, okay, well, let's look at higher dimensional tori, right? So I can take X as an abelian variety, meaning X is just some kind of n torus that also happens to be an algebraic variety. Right, so I don't have necessarily a good way to draw that picture, but it turns out that these guys are also codar dimension 0. Okay, another, if I want to go up to higher dimensions in a different way, I could also think about surfaces, right? Going up from curves, I could think about surfaces, and the particular class of surfaces that I'll mention are called K3 surfaces. So these are simply connected surfaces that have the property that if I want their canonical bundle to be trivial in a sense, right? Because I want this. I guess I didn't give you the definition of what codar dimension means, but in any case, it turns out that this in this instance will mean that I want the space of global sections of two forms, two being the dimension of my variety, to be one-dimensional. So generated by some single two forms. Okay.
And that's an orientation, no? Or
And that's what? Sorry.
an orientation or no on the surface?
It has an orientation.
Yes.
Yeah.
Okay.
Yeah.
Thank you.
Okay. And now this is surfaces, right? If I wanted to go up, if I wanted to generalize this definition even more to higher dimensions, one way that I could do that is to consider what are called hyperkähler manifolds. So I just take word for word my definition of K3 surfaces, but I no longer require that the dimension be 2. So here I have dimension x is n, but everything else is the same. I'm simply connected, and if I look at the global sections of my space of 2 forms, this is generated by a single non-degenerate symplectic form. Okay, and it turns out that this condition of this, do I have colors?
They're there in the table.
But manifold means there's no singularities, right? It's not writing that there's no singularities.
A priori, yes. I mean, in fact, yeah, I mean, because of, being an algebraic geometry, I do often sort of degenerate to some kind of situation where I do allow singularities.
Yeah.
But yes, I mean, let's say for the moment, smooth.
I think the word manifold is in the Riemannian geometry setting. The one that that locally looks like a patch.
Yeah, that's right.
Yeah. Okay. And I mean, recall that this word hyperkähler manifolds is in the title of my talk, so this is some kind of important definition. So I'm going to take a minute to sort of dwell on it. But it turns out that this condition right here, this condition of having the space of global sections of 2 forms on your variety be generated by a single non-degenerate 2 form, this is a super strong condition. Like the existence of this special 2 form right here is super strong, whether I'm in the context of K3 surfaces or in this higher dimensional setting. And this imposes a lot of kind of unexpected restrictions. And so in particular, this imposes the restriction that the dimension of my variety is actually even. What else did I want to say? It imposes the restriction that this canonical bundle of my variety is trivial. And for these varieties, we actually have this very strong theorem, which we call the Torelli theorem, which I won't sort of state in full technicality here, but essentially says that that if I'm given that this hyperkähler manifold, once I fix the dimension and a couple other numerical invariants about this hyperkähler manifold, it's determined up to isomorphism by just looking at its integral, second integral cohomology. Okay, so that a lot about the variety itself can be read off of looking at this lattice. Okay.
Are you putting some compactness conditions or no?
Yes. Yeah.
Okay.
Okay. And I'll just briefly say, the last bucket of varieties that I mentioned were these ones where the Curvature dimension is equal to the dimension of the variety itself. Right. So this case when the dimension of x is equal to the Curvature dimension of x, right? And such varieties have a special name called general type varieties. And this is kind of the wild, wild west of algebraic varieties. Like there's sort of utter chaos and we have no idea really what's going on here in terms of any sort of classification or description even of most general type varieties, right? Somehow, if you imagine any sort of set of equations, this by definition gives you something which is not general type. And so, I mean, that in a non-technical sense, right? I just mean like somehow if your brain can think of it, it's probably not general type. And so, you know, in general, the examples of general type varieties that we know are a bit more complicated to come up with. But if we want some examples, these include things like, you know, so we saw that we can make, oh, I guess I erased it. Oh no, here it is. We can make code-hour dimension minus infinity varieties by taking low degree hypersurfaces in projective space. Well, if I take high enough degree hypersurfaces in projective space, I get something general type. So if I look at YD inside of Pn, for d greater than n plus 1, this is general type, right? And so in a sense, you can think of this statement as saying like most hypersurfaces. Did I start? Oh, sorry. Did someone say something?
Sorry, yes.
Yeah.
What is YD?
Y is a degree d hypersurface in Pn. A homogeneous polynomial of degree d defines a hypersurface in projective space, right? And so this statement is saying most hypersurfaces in projective space are general type, right? If you close your eyes and you pick a hypersurface, it's going to be general type. In the same way that, you know, if you close your eyes and you pick a complex number or a real number, it will be irrational.
No, I'm confused. Now I can come up easily with such examples, but you said before the first thing that you come up.
No, you're right. You're right. I mean, and it's sort of in practice though, if you try to create more complicated examples of general type varieties, it is often challenging. But the other sort of canonical examples, if you will, of general type varieties are things like moduli space, come from moduli spaces. So if we think about moduli spaces of smooth curves of genus G, for instance, this space is general type. And same for, you know, if we think of the moduli space of abelian varieties of dimension G, these are both, you know, algebraic varieties, quasi-projective varieties, which as G gets sufficiently large, become general type. Okay. So this was a bit of a lead up into just, yes.
Sorry, I'm a bit confused.
Yeah.
Because you said that being Hyperkähler means that the canonical bundle is 0, but in surfaces, the canonical bundle is that omega 2. So
Sorry, when I wrote this, I mean, it's trivial. So it generates like a one-dimensional space of global sections. Yeah, exactly. Okay, so this is just to kind of give us a way of thinking about these different classes of varieties, having code-hour dimension minus infinity, having code-hour dimension 0, or being of general type in this sense. And what kind of turns out to be the miracle of so maybe let's say this way. Why are K3 surfaces and Hyperkähler manifolds and abelian varieties for that matter so studied in algebraic geometry? The reason they're so studied is because it turns out they have a lot of extra structure, as well as, which we kind of see popping out in some of these restrictions, for instance, imposed by the existence of the symplectic form, but also because they somewhat remarkably turn out to have a lot of unexpected relationships to other classes of varieties in algebraic geometry. And so somehow the theme of my talk today is to think about and formalize a little bit some of the ways that we can see the way that Hyperkähler manifolds, this class of examples of varieties of, you know, flat curvature or code-hour dimension 0, are actually related to both varieties of general type and varieties that are of code-hour dimension minus infinity. So how we can go from a Hyperkähler manifold to produce something both in this bucket and in this bucket. Okay, so what are some first examples that we see this kind of behavior showing up? So the classic example of a K3 surface that maybe I should have mentioned at the outset comes just from taking a double cover of P2. So this is an example of a K3 surface. And how do I get this K3 surface? So I'll call my K3 surface X. And I can produce X as a double cover of P2 ramified along a sextic curve I'll call gamma. Okay. And so what you'll notice, right, is that here we have our K3 surface. We have our P2 is our variety of codar dimension 0. But we also have along for the ride. Sorry.
Infinity?
Not yes. Thank you. Yes, minus infinity. Right, and along for the ride, we also have this sextic curve. Sextic meaning described by an equation of degree 6. Gamma, right, which is sitting inside of P2, but is the ramification of this map. And this sextic curve, as a curve, we can use our genus degree formulas to see it's planar, to see that this guy has genus, I think 10, but in particular it has genus greater than 2, and so it's of general type. Okay, and so then the other classic, or if we want to now move up a little bit in dimension and start thinking about these hyperkähler manifolds and what are the classic examples that we have in mind when we think about hyperkähler manifolds, the first example that people usually see is if I look at a degree 3 hypersurface inside of P5. So this is called a cubic fourfold. Cubic for the fact that it's degree 3, fourfold because it's dimension 4. And I look at, I'll denote it as f of y. This is going to be the variety of lines on this y. Right, so the points of this variety, f of y, are parameterized by choices of lines lying on my original hypersurface. Okay, and it turns out, this is a result due to Bouville and Donaghy, that this thing, f of y3, is a hyperkähler fourfold. Okay, so this variety of lines turns out to have this property. And so, how do we, from this idea, what are the other kinds of examples of hyperkähler manifolds that we should have in our minds when we think about producing hyperkähler manifolds? So there aren't so many different classes of examples. So the first class of examples that people know are if I take a K3 surface, so S is a K3, and I consider the Hilbert scheme of n points on that K3 surface, right? So points of this variety are schemes of length n on this K3 surface. And I consider deformations of this. So I take my Hilbert scheme and I deform it. Turns out that is always a hyperkähler manifold. So this is deformations, let's say. And this is called a hyperkähler manifold of K3, let's call it K3n type, because I'm deforming this K3n Hilbert scheme. And so, in fact, this example that I just gave of considering the Fano variety of lines on a cubic fourfold, it turns out that this thing is of this type. So it's a deformation of a Hilbert scheme of 2 points on a K3 surface.
If the surface is smooth, are these smooth as well or no?
Yeah.
Okay.
Yes. Okay. But how might I produce other examples of this type that aren't literally the Hilbert scheme? One way is by considering You know, so the Hilbert scheme is produced by considering you can think of this as some kind of moduli space of choices of schemes of length n on the K3 surface. I can generalize that picture a little bit and instead consider smooth moduli spaces of sheaves on the K3 surface. And it turns out that as long as this guy is smooth, this gives me an example of a Hyperkähler manifold of this type. Okay. There are, you know, some other ways to produce classes of Hyperkähler manifolds, and I sort of prepared to list them, but maybe I won't. So let's just say this is one way to do it, and there are some other sort of generalizations of this in one way or another, you know, relaxing either this smoothness criterion or using abelian surfaces instead of K3 surfaces, where you can do something similar and also get examples. But I'll maybe leave that alone. Was there a question? Yeah.
With deformations, what do you mean?
I
mean, like, yeah. No, actually, no. Like, how do you deform? Do you deform it as a scheme?
Yeah.
For a line or?
Over a line. I mean, not necessarily over a line.
Okay.
You know, you kind of pick a direction of the tangent bundle and you.
Okay.
So infinitesimal first order deformation.
Yeah, it's like no, okay.
So two are, you say, okay, two varieties are deformation equivalent if you can find a curve that is algebraic, and an algebraic variety
that parameterizes the whole.
Okay.
There are two fibers in this one family. Let's say it that way. Okay.
Then I understand.
Then you understand? Okay.
Good.
Okay. Okay. Okay, so you might object to this example that I just gave of these moduli spaces of sheaves as being, you know, a not very explicit way to produce, you know, to really sort of get your hands on such examples. And it turns out that there are much more explicit constructions out there, and they all sort of, I mean, not all, but largely they follow a similar kind of procedure as what I described here with this example of considering the variety of lines on a cubic fourfold. And so the procedure that you see is often you kind of, so you, how do I rewrite explicit constructions? So in fact, if you start with this same cubic fourfold, various other people have constructed, so you have, you know, this f of y3 is the lines on y3. You can also construct, I'll call it z of y3, some kind of variety of twisted cubics on y3. And you can do somehow various other kinds of geometric constructions that I won't say to this cubic and produce examples of Hyperkähler manifolds. Okay, and so if we and okay, so somehow we're starting with this cubic fourfold. We're producing these Hyperkähler manifolds via some sort of geometric construction. And it turns out that this relationship between the cubic and the Hyperkähler that we produce is often reflected at the level of derived categories. So if we look at the derived category of this cubic fourfold, it has some very explicit description, right? So it looks like I have a bunch of canonical types of objects related to it being embedded in projective space. And then I have this extra component, I'll call it AY, which is just defined to be the you know, the orthogonal of these canonical objects. This thing is called the Kuznetsov component. It was originally defined by Kuznetsov. Okay. And this AY, this Kuznetsov component, it turns out is a kind of category called a K3 category, meaning that it behaves like the bounded derived category of sheaves on a K3 surface. Let me just read that. Yeah. Okay. And so we saw that, you know, one way to produce examples of hyperkähler manifolds was to consider moduli spaces of sheaves on a K3 surface. And it turns out that you can formalize this to be able to do a similar kind of construction and consider moduli spaces of sheaves on a K3 category. And I mean, I'm not going to say any of the technicalities of how you do that, but just, you know, everywhere you see K3 surface, you insert K3 category instead. And it turns out that, right, so we saw that we can build examples of hyperkähler manifolds that are deformations of Hilbert schemes of endpoints on a K3 surface. It turns out, so this is due to Bayer and Macrì, they showed that in the example of this cubic fourfold, I can, and maybe let me just say, yeah, Li Pertusi and Zhao as well. I can construct basically all these known examples of hyperkähler manifolds built from the cubic fourfold as moduli spaces. So this f of y and this d of y that I mentioned from considering twisted cubics on y as well as lines on y, I can build these as some kind of moduli space on this K3 category. Okay, so I mean, this is all maybe a bit fancy, but I mean, the point is just to illustrate somehow that right, what's the point? Is that you have this, you start with this hypersurface and projective space, you build a hyperkähler manifold. This guy was Fano. So you start with a Fano, you build a hyperkähler manifold using some sort of geometric magic, and then you can somehow recover the relationship between these two objects at the level of the derived categories. Right? That's the whole point of this discussion, is that the derived category somehow sees this geometric construction and sees you by looking at the derived category of this y, you somehow see the hyperkähler manifold x.
So, and the manifold arises as a moduli space on the Kuznetsov.
Yeah.
Okay.
Okay. Okay, so, and I won't write down, but there are many other kinds of examples of a similar phenomenon where you start with a Fano manifold, a Fano variety. You do some sort of geometric magic to it, usually, you know, parametrizing subvarieties of some subsheaves. I mean, anyway, parameterizing some sort of objects related to this choice of Fano, and that gives you a hyperkähler manifold in various explicit examples. And so the real question motivating the talk today is the question of, you know, can you formalize this relationship between the Fano and hyperkähler in some kind of more general setting, right? Not just for explicit examples, but for some larger class. You know, so in general, and also in arbitrarily high dimensions. right? So somehow here you're kind of starting always with this fourfold, and you do something to it, but that kind of limits the options you can produce. And I'll say as well, as a remark, that if I do some kind of magic, so I start with my cubic fourfold, I do some kind of magic, I produce some kind of Hyperkähler, which is a deformation of a Hilbert scheme of endpoints on a K3 surface. This gives me some kind of unirational parameterization of the moduli space of such Hyperkählers of K3n type. Okay, but much like, so this implies that this is unirational, meaning in particular that the codire dimension of this moduli space is minus infinity. Okay, but much as in the case of the moduli space of genus G curves or the moduli space of G-dimensional abelian varieties, we know that for moduli spaces of Hyperkähler manifolds, as this n gets higher and higher, the moduli space becomes of general type, right? So we don't really expect in general to be able to do such a construction for arbitrarily high dimensions, right? We expect that such an explicit kind of thing can't work forever. Right, so we know that this guy, K3n, is, maybe let me write this. This guy is general type for n sufficiently large.
But did it always, we now talk about the three classes, and minus infinity, the class and the full dimension. And what about all those things in between?
Yeah, I didn't talk about those.
Okay. Okay.
Those are sort of more mysterious.
More than general type.
Well, I mean, I think if they're more mysterious, as in like if I say to you, give me an example of a variety of codire dimension 17, yeah, you're gonna have a kind of hard time.
Okay.
But what?
Yeah, P17.
Yeah. Okay. Well,
no.
P17. No, that's a projected space.
But 17 with Y17. So you can take those with curves. So
yeah, okay. You can, well, yeah. I mean, so you can do some kind of product construction.
Okay, yeah.
But like, somehow if I say, what are all, like, you classify for me all the varieties of codire dimension 17, like, we don't really.
Because now this construction jumps from this codire class of minus infinity to the codire class of 0, right?
Yes.
Then there are constructions as well.
Certainly.
So that you're out of this minus infinity, you can go higher by doing products and.
Sure. Certainly, it's possible to construct varieties of any codire dimension.
Okay.
In particular, just by doing stupid tricks.
Okay. Yeah.
Like what was just mentioned, right? Like by taking products with curves or whatever.
But for the hypersurfaces, it was a very sharp bound, right?
Yes.
From 0 to the full thing, nothing in between.
Yes.
No, but
there are things in between. If you look at it, jumped from less than or equal to n to strictly greater than n plus 1.
So there's a one.
So that n plus 1 is there's interesting things that can happen there. Okay.
Exactly.
Okay. I didn't say that maybe this result is due to this thing about the codire dimension of these moduli spaces being, the dimension of the variety as n tends to infinity. Okay, so the theorem I'll write down now. The main theorem I want to talk about today is the following. So this is work with myself, Emanuele Macrì, Kieran O'Grady, and Giulia Saccà. And what the result says is, so if I have X is a Hyperkähler manifold. H is a choice of ample class on this Hyperkähler manifold, such that, so X is of K3 n type, in the sense that I gave, meaning it's a deformation of a Hilbert scheme of endpoints on K3 surface. And the square of this ample class, and so the is 2, using some kind of quadratic form that we have on the lattice of the second integral cohomology of this variety. So this is, maybe I'll write this as ample. Right, so I need such a Hyperkähler manifold, and I need this square to be 2. And why I want to specify that the square is 2 is somehow this is the lowest thing possible. And so it means that my varieties will move in a maximal dimensional family. Okay, so you can sort of make versions of this theorem for other situations, but this is an instance where you know you kind of have a very large family.
Square?
So this is there. So if I look at the lattice, maybe the lattice H2XC, this is a lattice. It has a quadratic form on it called the Beauville-Bogomolov-Fujiki form. Yeah. And when I say H squared, I just mean the quadratic form of H paired with H. Okay. Okay, and so the theorem says that there exists a unique involution, which I'll call tau, x to x, such that if I look at what this involution does on the second integral cohomology of my variety, so tau star acting on this second integral cohomology, if I look at the fixed locus of that, it's just H. So meaning there's some involution defined by this property. And the reason for that is this Torelli theorem that I gave way at the beginning, which somehow says that, I can lift to the variety anything that's happening at the level of the lattice. So I have this involution, which I define at the level of the lattice, and then I can actually lift it to the variety. So I have such an involution, fine. And then such an involution exists, but the main sort of interesting thing is that this tau has the properties that one, I need to say one more thing. So in this lattice, I want that the divisibility of, okay, maybe I'll say something in a second. Okay, this tau satisfies the property that the number of components of the fixed locus of tau acting on the variety itself. It turns out this is a smooth variety, and its number of components is equal to the divisibility of H. And so what is the divisibility of an element of a lattice? That's just the smallest, if I take my element and I intersect it with every other element of the lattice, that generates a subideal of Z, or an ideal in Z, sorry, and it's the generator of that ideal. So it's like the number that divides every number given by intersecting my element of the lattice with every other element of the lattice. Mm-hmm. And in particular, that means that whatever the divisibility is, it has to divide the intersection of H with itself. And so if I'm specifying, I erased it, I guess, but that this number is 2, which I wrote originally, right? If I'm specifying that this number is 2, that means that this divisibility automatically is either 1 or 2, right? So this is equal to 1 or 2. So the number of components is either 1 or 2, determined by the divisibility of this element, fine. But the sort of more interesting part maybe is that if I'm in the situation where the divisibility of H is actually equal to 2, then one component, then I have 2 components by part 1, and one of those components is Fano. Right, so in a sense, this is reversing this construction that we saw before, right? We saw this construction where we start with a Fano, we do some geometric magic, and we produce a Hyperkähler. This is saying, given any Hyperkähler, I don't have to know any sort of explicit characterization of that Hyperkähler. as long as there exists some class of square 2, I can produce for you a Fano subvariety of the ambient hyperkähler. Oh, and this is, maybe I should say, it's known that this fixed locus is of dimension n. All the components are of dimension n. So my variety is of dimension 2n. So half the dimension is a Lagrangian submanifold of that. The fixed locus is a Lagrangian submanifold, has either 1 or 2 components, and in the situation that it has 2 components, one of those components is Fano. And then as a conjecture, so we make a few conjectures.
Is the tau, how does the tau relate with the symplectic term?
It's anti-symplectic. So meaning it sends the symplectic form to minus itself. Right, so maybe I'll just write on the board what I said in words, right? But the point is now we're starting with a hyperkähler manifold, and we can produce a Fano in some kind of canonical way, right? Not using any sort of magic involving equations, but in some way that deforms in families.
As say deforming in families, as in if you deform X, the Fano associated.
If you deform, right? So as you deform X together with the choice of ample class, that deforms the involution as well.
Okay.
Right, and so then as you deform these guys, that deforms the involution, that then deforms this fixed locus of the involution, and in turn deforms this Fano. And so we make a couple conjectures as well, but this fits into a little bit of a bigger picture, which is, so one, we conjecture that whether I'm in the divisibility 1 or divisibility 2 case, one component of this fixed locus, meaning the other component, the one I haven't talked about, is actually of general type. And we can verify this in low dimensions. So we want it to be for all dimensions.
So if the diff of H is 1,
then there's only one component.
You expect this to
and
be
I expect that
type.
to be of general type.
Okay.
And if div of H is 2, there's 2 components. One we know is Fano, and the other we expect to be of general type.
Okay.
And then the other conjecture, which goes back to this kind of derived category picture I gave, is that this I said somehow that we expect this relationship between the hyperkähler and the Fano to be canonical in the sense that it's reflected at the level of derived categories. And so what we expect at the level of derived categories is that, so if we're in the situation of divisibility 2, so that we have this Fano component, right? So let's say, so F is our Fano component, then what we expect is that there should exist some K3 category, which I'll call A, embedding inside the derived category of the Fano, such that I can recover the hyperkähler X as some kind of moduli space of sheaves on this K3 category, right? So that it's not sort of, and the point of this is, right, as I said, it's to prove some kind of canonicalness of the construction of the Fano out of the hyperkähler. It's not just some random Fano that you're producing, but it's a Fano that really intrinsically sees the ambient hyperkähler.
Yeah. Is for generic X or for all?
It's a conjecture, so let's say for all. I can make my conjectures as ambitious as I want, right?
How strong is this diff restriction?
How strong? It's not really a restriction, right? Any element of this lattice, if it has square 2, then its divisibility is either 1 or 2.
Sure.
Some of the time it's 1, and some of the time it's 2.
Okay. Is it given that there's always something that has this?
Is there always a class of square 2? undivisibility to?
Yeah.
No. So
That's a restriction.
yeah, it actually gives us restriction on the dimension of x. So I need, maybe I should say that, right? In order to be in this situation, I need the dimension of x to be congruent to 0 mod 8. Okay, but again, we can, this conjecture, the result that I stated earlier about this z of y3, this variety of twisted cubics on a cubic fourfold, it turns out that all hyperkählers of K3 4 type, so hyperkähler eightfolds, or deformations of Hilbert schemes of 4 points on a K3 surface arise this way. And so this result that I stated over here that says that the hyperkähler, I guess I wrote it somewhere, the hyperkähler can be realized as a moduli space of sheaves on that K3 category is in a sense, verifying this, the first case of this conjecture. So that the first case is known to be true through this work of other people. But the hope would be that this holds more generally for this broader class of Fano varieties. Right? These Fano varieties whose dimension is increasing with the dimension of the hyperkähler. Right? The dimension of the Fano is always half the dimension of the ambient hyperkähler.
Is this the only evidence? Or
Yeah, it's the only evidence. It's an ambitious conjecture. It's a conjecture that's less supported by evidence and more supported by one's feeling that, like, if anything is right in the world, this thing should be true. So,
is it an ambition to like classify all hyperkähler manifolds or just?
Yeah. I mean, there's kind of a huge corner of the hyperkähler manifold universe that's devoted to people trying to come up with new examples. And in particular, ideally, I mean, I think so I should say it's known that the class of Fano varieties are bounded in the sense that if I specify the dimension of the Fano, there's only finitely many deformation classes of Fano varieties of that dimension. And it's kind of believed that that is true for hyperkähler manifolds as well. And in fact, in terms of known examples of Fano varieties, there's huge libraries of examples of Fano varieties. Like there's a whole other universe of algebraic geometers who spend their time trying to come up with and classify examples of Fano varieties. And so they have this enormous collection of Fano varieties they've found. By contrast, in the hyperkähler land, we have almost no examples. And so I think it's commonly believed that there are finitely many deformation classes of hyperkähler manifolds, and like maybe we found them all. That's like maybe another class of people believe that. But in any case, it's certainly expected that there are not very many. I've now forgotten what your question was, but
That's a basic question of hyperkähler. It wasn't really.
Whether people try to find new examples or classify old examples. Yes, the short answer to your question is yes. Okay, I have till 4:20.
Yeah.
Okay, I'll just say like a few words about the proof, I guess. Are there other questions before I say a few words about the proof?
Are K3 categories smooth?
Are they smooth as categories?
Yeah.
Yeah.
Okay.
Yeah.
Okay.
Yeah.
So so for you, Fano is smooth, eh? Or not?
Yeah, for me the Fano is smooth, correct.
So do you know if the other component is smooth?
Yeah. So it's a result of Beauville that any anti-symplectic involution on a hyperkähler manifold has smooth fixed locus, a smooth Lagrangian fixed locus. So you know from the outset, just from Beauville's result, that the fixed locus is some finite number of smooth components that are disjoint. Okay, so let me say a tiny little bit about how the proof of this theorem goes. Okay. So the proof idea is the following. So we want to find, I said, what's one easy way we can produce examples of hyperkähler manifolds of K3n type? It's using these moduli spaces of sheaves on an explicit K3 surface. Okay, so what we want to do is we want to find some explicit moduli space of sheaves on some explicit K3 surface where you can check the result. Because there, this involution, which we defined in some kind of mysterious way, on our particular example, you can define it explicitly. And the explicit way that we want to do that is we want to build our K3 surface as a double cover of P2. As I said, ramified on a sextic. So it's the sextic curve at P2. And now there's an obvious involution on this K3 surface coming from this double cover, right? So this K3 surface has this involution on it. And what we want on this, so this particular moduli space that we're choosing, we want to choose it so that this involution, the involution on the moduli space, which is described this way, happens to coincide with this, with the one induced by this involution, right? So you want your involution here to be induced by this special involution coming from the double cover, right? And moreover, this is a bit delicate because you also need to make sure that then that involution sort of deforms in the way that you want. I mean, that it really does coincide with the one we've defined up here. Okay. So it turns out this isn't quite right, but kind of as a test exercise. Let's think about what would happen. Like, so this isn't quite the moduli space that we use, but just for our brains, let's think about the particular example that this special moduli space. What if it were just literally the Hilbert scheme of, let's say, 4 points on this degree 2 K3 surface, right? Then what would the fixed locus look like of the involution on this Hilbert scheme of 4 points on the degree 2 K3 surface? Well, how do I pick 4 points on my K3 surface that are fixed by the involution coming from this double cover P2, right? The first way is I pick 4 points on my ramification, right? I pick 4 points on my ramification curve, and all of those are then fixed by my involution. So then as a set of 4 points, it's fixed by my involution, and I get a component of the fixed locus, right? Or I could pick 2 points on my ramification curve, and then 2 points, 1 point on P2 minus that curve, right? Because this point, I pick 1 point here, not on the curve, it pulls back to 2 points under this double cover, and then the 2 points on my curve give me 2 points, so I get a total of 4 points on my K3 surface, right? Or I can just pick 2 points on P2 minus my curve, right? And so, again, this is sort of a cartoon picture, but what you'll notice is, so now I have 3 components. This guy, sim2 of P2, is Fano, right? It's just sim2 of P2. And this thing, sim4 of a general type curve, this thing is general type. So I have these 3 components, my Fano component, my general type component, and this guy, turns out this guy sort of doesn't deform. So it exists on this component alone, but it won't exist on like other guys in the moduli space. And I said this isn't, in fact, really the precise moduli space we want to choose, but it at least sort of helps us see how we might do this, right? If we pick another moduli space where everything deforms nicely, then we could imagine we could sort of do a similar sort of argument to see these two special components pop out, right? And then once we've checked the result on some special example, we just need to check, right? So here's our moduli space, MK3 and 2, Q. So this is the moduli space of K3n type hyperkählers, the class of square 2 and of divisibility 2. And we've checked our result for one guy in the moduli space. And so then the second part of the proof is to show that if the result holds for this guy, it holds in a small disk around. And that's really where the result sort of runs into some technicalities. But once you show that it holds in a small disk around, the thing that you checked it for, then you've proved it for everything in the moduli space, using the fact that this moduli space is known to be connected. And so that's the proof idea. The end. Proof done. So, and I'll stop there.